A tutorial on multiple regression. We'll start by checking the linear relationships between the predictor variables. We have 5 variables in our data set. We have our ID variable, 3 quizzes, and the final grade in a stats course. We're interested in examining whether the 3 quizzes predict the final grades in the course. And in order to do this, we need to run a multiple regression. So we have 3 predictor variables and 1 outcome variable. So 3 IVs, 1 DV. So before we can actually run that analysis, we do need to check our assumptions. We can assume at this point that the data has already been cleaned and screened for outliers and impossible values and response sets. So we'll just focus on the assumptions related to the analysis specifically. So the first assumption that we're going to check is for linearity, and what we're checking is to make sure that there's a linear relationship between the quizzes and the final grade in the course. So to do this, we're going to create a scatter matrix, which is essentially a whole bunch of scatter plots at once to look at all of these different relationships visually. So we'll go down here to scatter plot, and then instead of clicking on this one here, we're going to click on the matrix down here and drag it up. So what this will give us is a series of scatter plots representing all the relationships we choose. So we're actually going to put all 4 variables in here. And actually, I don't think we can move them all at once. So we'll have to do them one at a time. So we had quiz 1, quiz 2, quiz 3, and quiz 4. And final grade rather. Once everything's in here, we can move on. So we click OK. And now we have our scatter matrix. So this is a lot like a correlation table where essentially this top of the screen is going to be the mirror image of this, except that it actually flips the x and y axis, or the x and y bars. So essentially it's the invert of what's up here. So we'll just focus on the top, and essentially we're looking for any unusual patterns that suggest a nonlinear relationship. So a cloud is fine, a line like this is fine. It just means there's a strong linear relationship there. However, if we were to see kind of like a V or an inverted V or a U or something that kind of took an S shape, that would be a problem. But as long as we can be pretty confident that it's not nonlinear, we're good to proceed. So in this case, we're interested in stats grade and each of this ones. So we can just look at quiz 1 with stats grade, quiz 2 with stats grade, and quiz 3. And we have linear relationships in all 3. So we're good to go with our linearity. Next, we'll examine multicolinearity between predictor variables. The next thing we need to check is our assumption of multicolinearity. So although we're looking for a linear relationship between each of the IVs and their DV, we do want to make sure that none of these variables are too closely related to each other. Otherwise, it would be impossible to distinguish what the contribution of each of these variables was independently on the dependent variable. So we do need the variables to be a little bit different from each other. So to check for this, again, we're going to go to Analyze, and this time we're actually going to go to the Regression tab and select Linear. So this is actually a little bit, it's not a long process, but we need to run this analysis for each of the independent variables that we're looking at. So in our case, we have 3 of them, quiz 1, 2, and 3. So we're going to do this 3 times. So first we'll do is assign one of them randomly as the dependent variable, and the other 2 will become the independent variables. And then what we need to do is go up here into statistics. We can unselect estimates, unselect model fit, and we're looking at collinearity diagnostics. So what this is going to do is look essentially at the relationship between quiz 2 and quiz 1 and quiz 3 and quiz 1 and make sure that there aren't any issues. So we click OK. And the only table we need to worry about is the table right here. So what we're looking for in the tolerance statistic is that the values are higher than 0.2. So we have 0.778 for both. So we have no issues here. Both are above 0.2. And then the VIF, we want the value to be no higher than 3 ideally, or 5 is kind of the borderline, and 10 is the absolute max. So if you're between 5 and 10, there's a bit of an issue. Over 10, definitely an issue. 3 and 5 isn't great, but under 3 is perfect. So in this case, we are good. So now we need to repeat this 2 more times for the other 2 variables. So we do analyze, regression, linear. This time we'll take out quiz 1, put it down here, and then take quiz 2 and put it up here. Rerun the same thing. Again, over 0.2, under 10, and even under 3, which is perfect. And then we'll just do it one last time. And then we'll take quiz 3. And again, we're good to go. So over 0.2, under 3. So we can be confident that we do not have any issues of multicolinearity between the scores on the 3 quizzes. Next, we'll look at homoscedasticity. Next, we need to confirm that our predictor variables have the same impact on our predicted variable for all levels of the variables. So essentially, in this example, what it means is that we need to ensure that quiz 1, 2, and 3 have the same influence on final grades, regardless of whether someone did well on the quizzes or poorly on the quizzes. So to test for this, we have to confirm that we have no issues with homoscedasticity, and we do this through the regression tab. So we're going to go Analyze, Regression, Linear. And here we just need to set this up like we're going to actually run the model. So we'll add all of our quizzes as our independent predictor variables, and we'll add our stats final grade as the dependent variable. So to check for this, we only need to look at one thing, and that is the plot of the relationship between these 2 variables. So in order to see the influence of everything at once, we're going to actually use the standardized version, so the Z-scores of the predicted variables and the residuals, so the error, essentially. So to do this, we're going to take Z pred here, and we're going to put it on our x-axis, and Z resid is going to go on the y-axis. And we'll click Continue, and that's everything we need to set up for this test. So from here, we'll get our output, and we can ignore everything except for this graph here. So what we need to do first is add a line of best fit, so essentially the regression line for this graph. So if we double click and then click on this, we'll add the linear line here, we can close it, and now we can look at it. So what we're looking for here is for the line to be pretty straight and for the scores to be clustered on both sides of the line and from the high and low end. So what we see here is a pretty good distribution on both sides this way. There's a little bit more stuff at this end than that end. However, we do see a nice kind of cloud of data, so we don't have anything to worry about. If we saw some patterns where, for example, there was something like this going on, a lot of scores here, a lot of scores there, that would suggest a problem. If we had a big U or a lot of scores at this end and a space and a lot of scores at that end, those would all be problems. But this really does just look like a cloud, and the line kind of goes right through it. So for the purposes of our analyses, we are good to go. Finally, we'll check for independent observations. Finally, before we can proceed with our multiple regression analysis, we just need to confirm that we have independent observations on our predictor variables. So that means no underlying relationship between quiz 1 and quiz 2, or quiz 1 and quiz 3, or quiz 2 and quiz 3. So to do this, it's actually very straightforward. We'll go to Analyze, Regression, Linear. This time, we don't need anything selected in the plots. We just need to click on Statistics, and then click on the Durbin-Watson analysis. So this will add an extra little output to our results, and we'll be able to interpret it quite quickly. So we click Continue, OK. And now the Durbin-Watson results end up in this table here under Model Summary. So we'll just look right here, and essentially anything, or values will always be under 4. Anything close to 2 is considered to be good, where 1 and 3 are kind of the parameters. So anything above 1 or under 3 is considered to be okay. In our case, our value of 1.697 or 1.7 is close to 2 and within that range of 1 to 3. So we can assume that we have independence of observations. Now we'll conduct a forced entry regression. Now that we've tested all of our assumptions, we can move forward with our multiple regression analysis. So the first thing we're going to check is whether these three quizzes, so quiz 1, quiz 2, and quiz 3, predict final grades in the statistic course. Since we don't have any underlying reason or past research to suggest that one of these quizzes already predicts final grades, we are going to treat all of them equally, and we're going to do a forced entry multiple regression. So that means that all of these will be entered at the same time, and we'll be able to compare them at that point to see whether they have a significant relationship with final grade in the stats course. So we'll go to Analyze, Regression, Linear. Again, keeping the model set up the same way where we have quiz 1, 2, and 3, and we are predicting our final grade. So now we can add a few things in the statistics. So we're interested in the model fit, the R-square change. We can unselect Durbin-Watson, and we can leave everything else the same. We don't need anything under plots. The save stuff, this is where you can do a lot of different work for identifying outliers and multivariate outliers, so we won't need that for this course. However, if you are looking to do slightly more advanced things, there's a lot of different functions here. Options, we will not use anything here, and bootstrapping we will also skip rather. So we can click OK and proceed with our results. So the first table we have is just a summary of what was run. So we ran one model, and we can see here that there were 3 variables entered, and you can see here underneath the table we have a dependent variable, which is stats grade. So this little b here just says that all the variables we requested were entered. We were able to do it. If there had been a problem, it would have notified us here. The first table gives us a summary of the correlation coefficient between the 3 variables. The variance explained by, or the effect size, so the R square here is the variance explained by these 3 variables. We've an adjusted R square, the standard error of the estimate, and then this section here is essentially comparing how much better the model got compared to no model. So in this case, when we're just running a model like this, the R square change is always going to be equivalent to the actual R square value because we're starting from 0. And the the F change is going to be the same as this F here because again we're starting from 0, and it'll have the same degrees of freedom as our model, and therefore this will match this. So when you're just running a forced entry regression, these change statistics don't actually mean anything. When we look at hierarchical regression, that's when this will come into play. So this table here, what you're looking at with the adjusted R square is that the value is similar to the regular R square. This takes into consideration some error and whether the model was generalized. And if you were to see a large discrepancy here, it might mean there's some problems with the error, but a couple points is nothing major, so we can suggest that this is a good indicator of our effect size. So next we have our ANOVA table. So we see here that we have an F value of 386.47, and for 222 degrees of freedom, this value is extremely significant. So P is much smaller than 0.001. In fact, so much small, it's so significant we can't even see where the next value is. So this next table gives us a summary of each of the predictor variables' contribution in our regression model. So what we have here is quiz 1, quiz 2, quiz 3. We have their unstandardized coefficients. Then we have the standardized coefficients, and then the t-tests examining how well each of these predictors predicts the outcome variable. So if we look here, we can see that in the unstandardized coefficients, the values vary significantly. However, but if we want to actually compare these with each other, we need to look at the standardized ones. So whichever one is the largest is going to have the biggest influence. However, the others could have a significant influence if these values here are significant. But in our case, the standardized beta coefficients for quiz 1 and 2 are actually quite small. So we have a standardized coefficient for quiz 1 of -0.02 And for quiz 2, it's practically 0, which means that these don't actually really have any kind of influence on the dependent variable. And if we look at their significant values, we see that that has been confirmed. So these are not smaller than 0.05. So therefore, quiz 1 and quiz 2 don't actually have any real influence on the dependent variable. Quiz 3, however, has a very significant relationship, and we have a value of 0.93 here, and this is a significant positive relationship given the positive value there. If you were to want to create the equation predicting final grades, this would be the constant. So you'd have y equals 50.34. And then since these are not significant predictors, you wouldn't necessarily have to include them in the equation, but you would have the slopes for each of the predictor variables. And that's actually everything we need to look at for this particular analysis. So in our case, we do have a significant model where our quizzes do predict the final grades. However, looking at each of the coefficients separately, we see that quiz 3 is actually the only one having a significant influence, and the others are not. And finally, we'll conduct a hierarchical regression. Okay, this time we're interested in examining, again, the relationship between quiz 1, quiz 2, and quiz 3, and the final grades in the stats course. However, in this particular example, we already know from previous research that quiz 2 is a significant predictor of the final grades. We know that from maybe the previous semester's course, since quiz 2 was administered to the students. But let's say that in this course, quiz 1 and 3 were added for this semester. So we're not actually sure yet whether or not they will also have an influence on stats grades above and beyond what we already know will come from quiz 2. So if we want to do this, we actually need to run it as a hierarchical linear regression because we need to enter the quiz 2 first, and then we can add quizzes 1 and 3. So to do this, again, we're going back to the regression and linear tab. And this time we'll actually just click reset to restart everything. So our dependent variable stays the same. However, this time we do need to set up the analysis so that SPSS tests quiz 2 and then tests all 3. So to do this, we enter quiz 2 as an independent variable. And then you'll notice right here it says block 1 of 1. So right now we're asking SPSS to run one model. However, if we add a second block here by clicking next, we can add quiz 1 and quiz 3. And now SPSS will run what's in the first block at the same time as what's in this second block here. So we have block 1, which is quiz 2, and then block 2 is going to be quiz 1, quiz 3, and quiz 2 from block 1. So it's going to run two separate analyses, and this is how we conduct our hierarchical regression. So go back to statistics. We'll keep model fit estimates. We'll reselect our square change right here, and we can click continue. And then like in the forced entry regression, we don't need to actually select any of the other options, so we're good to go from here. So we click OK, and SPSS generates our results. So what's changed now is that SPSS has now run two models. So this is block 1 and this is block 2. So we can see in block 1, that we have just quiz 2 as the independent variable. And then block 2 indicates that we've added quiz 3 and 1, but it's automatically going to run whatever comes before it up here as well. So everything has been entered. And again, stats grade remained our dependent variable. So this is where the change statistics get interesting. You will notice that we have two values for absolutely everything. And essentially, these change statistics here for the first model, so block 1, represent the difference between no model and the model we ran. So this value here is going to match that value there. This F here is going to match this F there, etc. However, model 2 is now comparing the model that we ran with the new model. And so this value is going to be the difference between these two here. And this value is the difference between these ones here, however, with a different error term. So it's not going to calculate exactly like we see it. It has to take into account that the error term changes. And then we're looking at different degrees of freedom for both values, and an additional test of whether or not this is a significant difference. So when you're looking at these two models, you might be wondering, okay, well, which model do we use? And actually, everything comes down to this value here under significant F change. So if we have a significant value under our lowest model here, which is 2, it means that model 2 is significantly better than model 1. Just like when we looked at only one of these, having a significant value here meant that our model was significantly better than no model. So what we wanted to confirm in the first round is that our first variable predicted our outcome variable, which it did by this value here. However, we added the additional variables, and now we want to confirm that this model predicts the outcome above and beyond what the first model did. And since we have a significant difference here, we can conclude that that's true, and these change statistics show us by how much the model has changed. So we notice here that our R value, so our correlation coefficient, goes from a 0.43 to a 0.92. Our effect size, so our R square, goes from 0.18 to 0.84. And the justice R square again is similar. So we can see that our second model really accounts for a lot more variance here in the dependent variable than our first model did. So since this is the model we're going to go with, for the rest of the results we can actually ignore everything under model number 1, and we'll just be looking at model number 2. So let's scroll down here, and what we see is that we have essentially the same sort of thing here. We have two NOVA tables, except that the degrees of freedom have changed, and that's because this value is dependent on the number of predictors in the model. So our first model had only 1, this one had only 3. Since this is a significant, since this one's significantly better, we don't need to look at this one. So we have an F of 386.47, and for 3 and 222 degrees of freedom, this is a good model, since P is much smaller than 0.05. Then we can now look at the actual coefficients, and what we see here is that quiz 2 is a significant predictor of final grades when we just look at quiz 2. Okay, so we have, this is the unstandardized value, this is the standardized value, the t-test, and the significance right here showing that, okay, yes, quiz 2 significantly predicts final grades. However, once we add quiz 1 and 3, we see that this relationship changes. And essentially we're back to the relationship we had before, where quiz 3 and quiz 1 do not have a significant relationship and do not predict the final grades once we take into consideration quiz 3, which is actually accounting for most of the variance in final grades. So this is the model that we would have to interpret. So we cannot conclude that quiz 2 has a significant influence on final grades. We have to go with this one and conclude that it's actually only quiz 3 that has the significant positive influence on final grades in the course. And finally, excluded variables here is just a summary of what was not included in the first model, which makes sense. We didn't have quiz 1 and 3. We were only looking at quiz 2.